Hi, everyone. Welcome to our panel on silent data corruption. This is one of the key topics that we'd like to discuss today in the context of RAS, which is reliability, availability, and serviceability. I'm Jyotika Attavale, Director of Engineering Architecture at Synopsys. And with me today are three esteemed panelists. We have Rama Govindaraju from Google, Rob Chappell from Microsoft, and Amar Hagag from ARM. Welcome. Thank you for joining us. And I'll turn it over to you for your introduction.
Thank you, Jyotika. I'm Rama Govindaraju. I'm a principal engineer leading the effort for reliability of machine learning systems at Google.
Hi, I'm Rob Chappell. I'm at Microsoft Azure. Been there for 5 years. And my responsibilities are mainstream Azure fleet reliability, performance, and future technologies.
And my name is Amar Hagag. I'm head of quality of ARM's Silicon Solutions division, which is basically an attempt of ARM to get into the business of moving our customers, closer to final silicon, was more comprehensive silicon solutions.
Thank you so much for joining us. And we'll kick it off here with a few questions and just open it up for discussion. So just starting off with what is silent data corruption, or also called silent data errors, SDE. What does it mean? How does it manifest? And what are we really seeing, on our systems? So what is the signature, et cetera? So I'm going to open it up to you to weigh in.
Want to go first?
Yeah, I think basically the expectation that software engineers have is if something goes wrong in hardware, then there's a machine check that occurs. So there is a fail-stop mechanism by which the users are notified that something has gone wrong. If something goes wrong in hardware and there's no notification, and it can sort of lead to incorrect computation or corruption of data, that is silent data corruption, because there is no indication that the hardware is given that something has gone wrong. But in fact, it has miscomputed something that is against the specification of the architecture. So that, in a summary, is what silent data corruption is.
Great.
So Rama has done a great job expressing the way that we look at it from the cloud service provider angle. But this question actually was a subject of much debate within our work stream at the Open Compute project. So our three companies, along with 4 other ones, formed a work stream to work on this problem. It was, I think, about 2 years ago it was formed. And we actually spent many meetings just on this topic of what is silent data corruption. And the reason why it was complex is that there's kind of a classical definition of what silent data corruption is. And in that more classical definition, if there is an indication that something went wrong, viewed at the system level, so for example, an unexpected page fault, that isn't silent according to that classical definition, because there's an indication at the system level that something went wrong. And that kind of made sense when you were looking at limited systems and it was mostly closed. But when you look at it from a cloud perspective, our system is heterogeneous, it's multi-tenant, it's dynamic, it's colossal scale. So something like an unexpected page fault, relatively speaking, happens commonly. And the cause is almost never silent data corruption. So it's very misleading to say, well, that wasn't a silent data corruption. And if you're only trying to solve the truly silent ones, you're not really addressing the problem that we have. And so we debated and kind of went around, and we ended up with this definition that Rama articulated, where the way I think of it is silent data corruption means that the hardware was silent about the fact that it caused the data corruption or experienced the data corruption. And that's the way that we have defined it in our work stream.
Yeah, I mean, as a vendor, that's also the way I view it. It's basically an error that went undetected by my chip. That basically maybe our users, the data center providers observed or even didn't. So it's a silent error or user observable error that just went undetected by our hardware.
Great. No, thanks for sharing those perspectives, from the various different entities. And as we understand it, this problem has been around since the past 7 years. We've been talking about it. In the past, we used to talk about it in the context of radiation effects and soft errors, and now, we've been talking about it more in the context of manufacturing defects. So, any thoughts about what progress has been made to date to address this challenge, and what still needs to be done?
Yeah, so I've been at this problem for almost 7+ years now. So since the beginning, trying to convince the vendors that, hey, there's a real problem here, to them at least now acknowledging the challenge. And I think the reason it's not been solved in the sense that truly we can put this to rest in the last 7+ years, is because it's a very hard problem, right? So these manufacturing defects are very hard to diagnose, happen sporadically sometimes. There's also aging and degradation issues. You can sort of observe this much more easily at this kind of scale we operate, and the kind of workloads, diversity that we have, that we run. So I think it is very hard for the manufacturers to reproduce that kind of an environment to get to root cause. So there are challenges at many levels in terms of how do we solve this holistically. Progress has been made. I'm not going to say progress has not been made in this last 7 years. Progress has mostly been made in trying to improve detection methods, screening methods, or building more resilience in software. I think all those areas have made substantial progress. But the scope of the problem is continuing at the same scale that we had seen 7+ years back. Maybe our methods have slightly improved, but this needs a holistic solution, both at the architecture level, the DFT methods, the tools, and the software systems to be more resilient to in identifying and localizing this. There's a huge amount of inertia of existing code that has to be enabled for this, right? So we need more research in this space because this needs a more holistic solution, and new ideas, creative ideas have to be brought to bear. I think doing more of what we have been doing in the past will not significantly move the needle. So it's a very, very hard problem where I think a lot of research and end-to-end solutions need to be developed. So I think there is progress in some parts, but a lot more still needs to be done here.
Interesting.
I think Rama said the magic word. The magic word is scale. So this problem didn't emerge 7 years ago. This has been around in the industry for decades. And I didn't mention this when I introduced myself, but prior to Microsoft, I spent 20 years architecting CPUs. So I also see things from the perspective of a chip designer. This is an old problem. The underlying types of defects that we're seeing, I hope Amar agrees with me, they're not fundamentally new. The methods and techniques for avoiding them and hardware features are pretty well known. Not saying that more can't be invented, but you can read papers from 50 years ago about techniques. The thing that's changed in recent times, and the reason why this has come back up, is because of scale. Is because Google, Microsoft, Meta, any big CSP with a huge installation has the volume to find these very low frequency events. And that's really the driving factor. Another thing that I think is interesting to point out is that back in my previous life, when I was a chip architect, we thought primarily about soft error when we were thinking protections. And I think that was almost out of convenience, because there are good models for estimating the frequency of soft error events. And so you can account it and project it, and you can come up with a plan, and you can have targets, and you can execute to those. But defects was a much different space, because the types of failures are very specific to the type of defect, and you don't really know what you're going to get, and you don't find out until you have high volume. And so the protections that we put in were more skewed towards soft error protections rather than defects. And so that, I think, has opened the door so that when you have CSPs at hyperscale and you have huge volume, we're finding all these really low frequency. And let's be clear, in absolute terms, the frequency is very low of these defects. But when you multiply by an enormous number, we find them. And that's what's caused it to bubble back up to the top as a challenge today.
Yeah, absolutely scale. So it's the data center scale, but also, these chips, are getting more and more complex. We're talking about 128 cores, a lot more memory, a lot more logic. So then the likelihood of actually having an SDC event, goes up.
Yeah.
And as Rob mentioned, the root causes haven't really changed. It could be, but in our mind, the way to actually address it is to be much more proactive. because we can't really be reactive to SDC. It's silent, so you don't really know when it occurs and how it occurred. And so to be proactive, you have to kind of understand what typically can cause an SDC. So things like droops, that can cause an SDC, and therefore I put a droop detect. Therefore I can at least mitigate against that particular cause. We mentioned defects. The better DFT that I put in place to that's timing aware, layout aware, cell aware. So it's the DFT that I've always had. I just make it much more aware of the design sensitivities. That way I can catch SDC events. Aging. Having aging sensors. So that's a way to also mitigate against SDC events. So I think the things that cause SDC haven't changed. What we need to do more proactively is just add more features in the design to avoid them from happening, given the scale that we're at right now.
Yeah.
And then when you consider the fact that anything you're talking about that's new, that you're putting into design, the design cycle is not short for complex IPs. We're talking about 4 or 5 years. So we've been talking about this like kind of more in modern times for 7 years. Building that awareness, building the understanding of the problem, coming up with a solution, putting it into a design and getting it into volume is not going to happen very quickly. I mean, that's at least the time that we've spent talking about it. And I think we're maybe, even though it's been 7 years, I think the awareness and the collaboration really has started in earnest in the last 2 years. And so the chips that will be impacted by that with features are further down the road. So as Rama pointed out earlier, most of the action, like in the here and now, of what can we do about this problem right now, is in the screening. How do we, build resilience? How do we do testing? How do we get the defective parts out of our fleets? But longer term, we're expecting that the future generations of hardware will have additional features to try to address the problems that we find in the silicon.
Great.
Just one additional comment, I think, to follow up on Rob's point about the low frequency. Let's say the frequency is of the order of 1 in 1,000 is a defective chip, right? The problem we have is these machine learning jobs are running on tens of thousands of chips in parallel. So a single job, a training job, is occupying tens of thousands of chips. And if 1 in 1,000 is defective, the job is being affected by multiple defective chips. And so these training jobs run for a long time, and these kind of corruption incidents can completely derail the computation. It's a huge expense.
Yeah.
So although if you look at, say, okay, it's only 1 in 1,000, order of 1 in 1,000, the new kind of workloads that are running in the data center are increasingly occupying a huge footprint. And the visibility of the disruptions these are causing are increasing day by day. So I think the challenge in some sense is multiplying very quickly, right? And so the need for the solution that is more holistic and rigorous, and I think Rob pointed out, the hardware design cycles are several years. It takes 4 or 5 years for a change in the design to materialize. And so what do we do tactically? How do we make our software systems more resilient? There is a ton of legacy software. How do we deal with this? How do we become better at screening these more holistically? I think requires research up and down the stack, right? From the architecture to the DFT, to the sort of verification methods, to the post-manufacturing methods, built-in software tests and other methods. Holistically, I think, what can the compiler do to detect these, localize these? There's a vast volume of research that is possible in the space.
I'm going to double down on that, because the problem, even not considering specialized things like training jobs, the problem is getting worse, because the scale is not slowing. It's not going to be very long before my fleet doubles. And then at the same time, that's just in terms of systems. At the same time, the integration is increasing. So there are more resources packed into a single part. There's more complex process. There's more complex manufacturing. They're reducing guard bands in order to save power. All of these things are stressing the system even more. And so we can't just solve the problem. We have to keep getting better generation over generation, even to stay flat. And that's really the challenge. We're trying to make up ground because the awareness wasn't there. And then just to stay flat, you have to continue to innovate and continue to address the problem.
Yes, very
Excellent point,
interesting.
yeah.
No, I fully agree with, and I think a lot of valuable insights here. I think key point is, the whole community needs to come together to address these challenges through the ecosystem, the IP providers, chip vendors, the
The tool
hyperscalers,
providers.
the tool providers, all need to come together as a community.
And one thing that Rob mentioned, you have to do it power efficient. It was a power efficient design.
Yes.
So for example, we're dropping the guard bands so that we can be power efficient. So we obviously have to solve for SDC while being cognizant of the fact that we still have to meet our power performance area.
Right.
Sure. No, great. Yeah, I think, and also I think the bridging that gap between industry and academia, because a lot of this is still research, so we can bring in the folks in academia to help out. I just kind of think back, when I started working at Intel about over 25 years ago, and since then, SDC was always used synonymously in the context of soft errors, right, and radiation effects. And then somewhere down the road, that switched context and is now being used, mostly focused around the manufacturing defect-induced issue. When did that happen, and what data do we have? I guess, or have we collected to really, make that alignment between SDC and the defect-induced issue versus historically the transient faults that we're worried about.
Yeah, so I think this came to our light about 8 years back, where one of our biggest services, Spanner, was experiencing some corruption, which we thought was a software bug. And we have multiple replicas of the tablets, and when they compute a checksum, each tablet compares its checksum, and the checksums were not matching. For the longest time, we thought this is a software bug. Usually these things are software bugs. But some of the best engineers dug in and couldn't figure out why these checksums were not matching until some very smart engineer noticed that whenever the checksum did not match, it seemed to be computing the checksum on a particular server. And then that particular server, when its logs were sort of dug into, you saw that a lot of kernel crashes were also happening on a particular core. And so that led to the suspicion that, hey, maybe that core is defective. And the smart engineer just dug in and figured out how to hammer that core and see if they can prove that this is actually defective. And lo and behold, he was able to prove that this chip is not always, complying with the architecture spec. And here is a small controlled test that can prove it. And so then we worked with the vendors who, for the longest time, said, no, this can't be that, or it must be something else, what have you, until, more evidence of this started to show. And then we started looking at other machines which were having a lot of kernel crashes. And then if they were concentrated on the same core, we found that this is far more widespread. And that's when we raised the alarm with the vendors saying, hey, there is something wrong here, and the numbers that we are seeing of these kind of things happening is huge. We do not know whether this kind of an issue existed in earlier systems, right, beyond 8 years back. Probably did, but we don't know the scale because, we didn't have the kind of footprint of those, and we didn't have the mechanisms to go back and verify and check those. Possibly it existed, may not be at the kind of scale and the frequency that we are seeing now.
Yeah.
But it's clear that in the last 7+ years, this problem has continued to sort of nag us, right? We have made some progress in some dimensions, but the overall scope of the problem, like Rob said, the scale of our data centers is sort of growing fairly rapidly. And the scope of the challenge, we are still trying to get our arms around it. And I do not see a light at the end of the tunnel yet.
Yeah.
Right. So a lot of research work has to be done to try and see what creative ideas we come up with to address this holistically for the entire industry.
Very interesting, yeah. I mean, that brings me to the question of how do we mitigate it at the chip level or the IP level, right? So I'm going to turn to you guys, Rob and Amar. Compared to our, legacy protection schemes, the ECC, parity, CRC, how do we need to address this differently? What else do we need to do on our SOCs and IPs to address this problem?
Yeah. So I'll answer your question and also build a little bit on what Rama said. I think there's somewhat of an aspect of convenience in that, as I mentioned previously, soft error rate was convenient to use as a currency for adding protections because we could model it well. And so what that ended up doing was predisposing all the protections that were put in against the kinds of errors that you get from particle strikes, which means you're primarily protecting memories. And so that is fine. You can catch defects in memories that way. But when you look at defects, there's a portion of those that are not going to be addressed by that because they're computation affecting.
Yeah.
And so that's probably the biggest thing that I think needs to change, is that it needs to be thought of more as a holistic problem. Like everything needs to be resilient, and not just the storage structures that can be affected by particle strikes. And so then you start seeing new types of techniques, which are again like known techniques, like computational residue or forms of redundancy. Like those things are there and they're known. It's just when you're looking at it as a chip designer, you're right, you have to make trade-offs, right? These things cost area, they cost power, they cost design time, and you're prioritizing those against your other things like performance and power efficiency and deadlines. So it was always a hard sell to like take RAS features through because they're costing you money, and yet it's not like necessarily producing a quantifiable benefit. So I think that's one of the biggest things that needs to change, is like there needs to be some kind of modeling or approach to accounting for the goodness that you get from those features as protecting against defects that corrupt computations. I'd love to get your opinion on that.
Yeah, no. On the chip design front, as mentioned before, we have to solve for it smartly because you have to be power efficient.
Yeah.
Especially when we talk about training, you have to be very power efficient. I can't just raise my vmin and say like, okay, well SDC is going to go away, but then my power efficiency goes through the roof. Or I can just add redundancy without understanding the area impacts. And so there's a lot of newer techniques that can be employed. Again, like the defects haven't really changed, or the type of causes that cause SDC haven't changed. So as we mentioned, noise can be mitigated through sensors that can cause SDCs. We talked about potential part degradation over time. If you have an aging sensor, you don't have to upfront raise your vmin, but adapt your vmin accordingly to avoid that from becoming an SDC problem. We also talked about kind of the DFT infrastructure, kind of just being smarter about detecting the type of things that can cause SDC. So I think approaching the problem smartly, without your impact to your overall power performance area, is the way to go. I mean, I can't just add protection everywhere because that's going to impact my power performance area. So I think that's the way we're looking at it, to proactively address.
Yeah.
So I just want to add maybe a couple of points here because I think cost came up. I mean, I think Rob is right that there are some existing methods that can be applied here, like residue arithmetic or lockstep execution. And every time I think this question comes up about cost of reliability. But the cost of not adding them is being paid by the customer, right? In downtime, in sort of software engineering time wasted or lost computation because of corruption at this large scale. If you add that up, I'm confident that it's far higher than the cost we are trying to save by skipping on these RAS features, right? I'm always told, lockstep is like going to double your computation cost. And my point is, look, if you design it in a manner such that it's dynamic, right, so that you can enable and disable it. So let's say the first 1 month in production or 2 months in production, I'll run with lockstep enabled, right? I'll pay the double cost, but it'll help me flesh out all the defective parts. And let's say the first month I flush them all out. Second month I didn't see anything, I can disable it. And if for the lifetime of a chip that let's say is executing in the data center for 6 to 7 years these days, roughly approximately, 1 to 2 months in the beginning and maybe 1 week every 6 months is perfectly reasonable cost. Right? But here's where the ingenuity has to come into designing these things in a dynamic fashion or in a cost-effective fashion. The cost problem can be solved through a lot of creativity. There's so many ideas people have on how to sort of minimize cost.
Right.
But first you need a solution. I think sort of backing away from even attempting the solution, I think is part of the problem here.
Yeah.
Like, residual arithmetic seems like a no-brainer. We should do it, right? Lockstep dynamic capability, no-brainer. Adding more structures in DFT for localization is so much more useful, because trying to debug after the fact, even if when we send the parts back to the manufacturer or to the vendors for root cause, less than 10% are root caused, because there's not enough telemetry for them to sort of decode what is happening. And of the ones that are actually root cause, it takes 8 months to a year. That is not scalable. So a more practical end-to-end solution has to be thought through, not just, okay, PPA, I have my PPA budget, I'm going to stick to it. But the PPA budget has to be consumed in the sort of the normalization of the area under the curve over the lifetime of that chip. And I think that holistic thinking is what is needed to effectively solve this problem.
Great. No, I think this is perfect. The last question I had was, some of the methodologies that we used to use, for example, fault injection or other approaches to measure vulnerability factors on the chip to identify which are those most vulnerable elements that we need to protect, because you can't protect everything on the chip. We make these trade-off decisions, optimizing performance with reliability. Can some of those approaches still be applied today in the context of SDCs for manufacturing defects? Can we still, and where are we with that? Do we have the fault models available to do those kind of experiments and collect that kind of data? And can we apply those methodologies, today?
So definitely we need, in order to estimate how much work we need to do at the chip design, in order to prevent SDCs, we need to understand vulnerability.
Yes.
And like how much flop hardening, we need to have, where do we need to put the protection? Again, I mean, I agree in general with what Rama's trying to say, is obviously you don't want to put PPA at the forefront and not understand the implications of having SDC, right?
Yeah.
Because that could actually have, some wider implications. But I think still having a good understanding of fault injection and vulnerability can at least help you optimize for those two, PPA and SDC. So there's been, obviously, progress in this area of trying to just, narrow down what parts of the chip are critical that need to be protected, and that's going to be key moving forward. Yeah.
Awesome.
Yeah, go ahead.
So
Go ahead.
Yeah.
This is something that I challenged the OCP workstream with, was to try to come up with a way to quantify the value, kind of like we have in the soft aerospace, quantify the value of different features with respect to defects. And the reality is that all defects are not created equally when it comes to their impact on computation. And you can see that in vulnerability, but you need a model, because as I think many of us have heard the phrase, if you can't measure it, you can't improve it. Well, that's kind of the situation with defects. At least that's the way I felt in my past life, is that you need a model where you can take credit, so to speak, for a feature. And if you don't have that grounding, and you're able to prioritize it in a data-driven way, it's very hard to convince yourself, I need to do this thing,
Yes.
lockstep, or the expensive features that, from an engineering perspective, are a heavy lift. You're not going to convince yourself to do those unless you have a way to measure the benefit.
Right, it needs to be grounds up approach. Like you first start, at the chip level, because eventually, while there's some system level solutions, you don't want to be over reliant on those. You want to kind of move the work upstream, to the chip, and so having the right user defined fault models, for your DFT, the right, fault injection capability, so what part of the design to protect, all that stuff,
Right.
helps you make or harden your SoC, so that you kind of lift some of the burden off of the system level protections.
Absolutely. No, thank you so much for that. I fully agree. Understanding the vulnerability and how that fault would progress through the stack and manifest at the output of the application is so critical. So I think that brings us to the end of our panel today. I just wanted to thank you all for, all of you panelists, for the very stimulating discussion and sharing your valuable insights. And thanks for being here with us today. And thanks to everyone for joining us. And look forward to continuing this discussion.
Can I make
in the
one more
future.
comment?
Yes, please.
I think that while we can be very proactive in trying to address SDC, there's definitely going to be a need to work, as as we can see here, between vendors and the hyperscalers. Because at the end of the day, that collaboration is what's going to,
Absolutely.
enable us. And trying to do it alone is not going to. Yeah.
Very important point.
Yeah.
Yeah,
It's a great plug
point.
for our OCP work
Yeah.
stream.
Yes.
Great. Awesome. Thank you so much.
Thanks, Jyotika, for
For having
inviting
us,
and forming this session. I think this is super useful.
It's been fun.
Thank you.
Thanks a lot. Thanks, everyone, and see you next time.
Thank you, Jolika.